താങ്കൾ വിളിക്കുന്ന വ്യക്തി ഇപ്പോൾ കോൾ
നമ്മെ ക്ലാസ് തുടങ്ങി. Hi everyone. So only three of you joined till now. So can you hear me? Am I audible? There's a slight light issue here. So I may switch off the camera if needed because tube lights are not working here. So let's see. So I'll slowly start the class now. Remaining people will join in time, I hope. So all of you got solution for week 5 assignments. Last week there was a doubt regarding some questions. So question number 5 exactly. One of you able to solve that problem? Was it clear and straight? In that case, I won't touch it. Otherwise, I thought I'll solve last week assignments in a quick manner, and we'll go through the this week's content and problems. What? I couldn't hear you properly. Okay, question number 5 exactly right. So to solve the other transport number and conductivity problems, then we'll go to that problem. Is that fine? So if you have already solved, you can directly say the answer. We won't waste much time in those problems. Okay. Yeah. So the question one was calculate the transport number of calculate the transport number of Li plus and Br minus. What was given when current flows through an infinitely dilute solution? The at 25 given ionic mobility of given given ionic mobility of Li plus and Br minus are 4.01 into 10 raised to minus 8 and 6.04 into 10 raised to minus 8 meter squares per volt per second. So how will you calculate? What is the answer? So this is straightforward question. What is the answer? What is T plus? What is T minus? How will you calculate? What is the formula? What's the formula relating ionic mobility and transport number? Yeah, what is the formula connecting ionic mobility and transport number? Anyone? U by U plus V. So what will be the transport number of cations? 4.01 divided by 4.01 plus 6.04 both into 10 raised to minus 8 into 10 raised to minus 8 will cancel out. The answer will be 0.4. So T minus will be 1 minus 0.4. It will be equal to 0.6. So this problem was easy and clear, right? So the second question was straightforward. Cell constant. Cell constant will cell constant for a conductivity cell. Conductivity cell. So this is clear also. Last week we have solved a number of problems where we So initially the resistance for a specific setup will be given. Using that we will be calculating cell constant. Using the cell constant we will be calculating the conductivity of another concentration of solution. So cell constant remains constant for a cell. Constant for a cell. Then Q3. Question number 3 was the conductivity of 0.056 molar Ag2SO4 is 0.0028 Siemens 0.08 Siemens or mho centimeter raised to minus 1. Then what happens? To conductivity? What happens to conductivity with dilution? Hmm. What is the relation between L and C? That is conductivity or specific conductance and concentration C. How can we relate? What's the formula? First pass. This questions will pass. Hello. Yeah. L is equal to lambda m into C divided by 1000. So L is proportional to C. So what happens? Conductivity it decreases with dilution. Clear? In case of molar conductivity lambda m, it increases with dilution because we have lambda m is equal to what is the formula? 1000 L by C. So lambda m is inversely proportional to C. So as we dilute it more and more, the molar conductivity will keep on increasing. So question 4 was just to understand the unit. What is the unit of cell constant? What is the unit of cell constant? Centimeter raised to minus 1. Yeah. Then specific conductance unit. Hmm. Mho centimeter raised to minus 1, or we can write Siemens centimeter raised to minus 1, or ohm inverse centimeter inverse. All are same. Okay. Then what is the unit of conductance? Conductance. What is the unit? Mho you can write, ohm inverse you can write, Siemens you can write. Right? So now we'll go to question number 5. So this one I'll elaborate a little because last week also students were asking doubts on this. So the question was Q5, a solution containing 3.94 percentage of copper sulfate was electrolyzed using a PT cathode and copper anode. After electrolysis, after electrolysis, the weight of cathode solution was found to be 65.79 gram, and it contains 0.809 gram of Cu, and the increase in cathode weight was 0.806 gram. Calculate the transport number of calculate the transport number of Cu. I have written it little badly, but is it readable? One minute. Do you see any difference from the question given in the website and this question? Whatever I written here, is there any difference? All of you, any of you solved this problem and got correct answer? I think now the answers are on. Anyone? So you may need time to write the question. But still, anyone got the answer for this one before the answer keys? Have you noticed something? So in the question given, yeah, in the question given in website, whatever NPTEL portal, I haven't seen the word solution. So now can you try to solve this? Because cathode weight has changed and there is two quantities are given. That was confusing. So I just gone through the problem given in class. So if it's the weight change in cathode solution is given, it makes sense as well as we will get the answer given in the answer key. So can you all try now to solve this problem? So it was not cathode weight change, it is cathode solution. Uh, because what we have done experimental determination initially before after electrolysis, we will weigh the solution and we will find how much copper is changed. So whatever copper is deposited, we can calculate using Faraday's law. Then from that we can directly say how much copper is calculate the transport number of Cu2 plus. So can you try now? Does it make sense now? The question. Are you trying to solve it or shall I start solving? Shall I start solving or you all want little time to solve? Yeah. Shall solve it. Yeah. So what's given in this problem? 60, 65.79 gram of catholite solution contains how much? 0.809 gram of Cu2 plus, right? So it's also given 100 gram of solution contains how much? 3.94 gram of CuSO4. This is before electrolysis. Then hence quantity of Cu2 plus in 65.79 gram of catholite before electrolysis, which can be written as 65.79 into 3.94 divided by 100 into 63.5 divided by 159.6, which is nothing but 1.031 gram. Is this step clear? Okay. So we haven't done just first step is in 100 gram, 3.94 gram. So in 65.79 gram, how much? Then we have to convert, it is copper sulfate 3.94. So we have to convert into copper. For that, we have taken the molecular atomic mass of copper and molecular weight of copper sulfate. So we'll get a gram of Cu2 plus. Then we can calculate weight loss is equal to 1.031 minus 0.809. This is nothing but 0.222 gram. So what is transport number? Transport number of anion is given by loss in annulite chamber divided by loss total loss in both compartments or both chambers. So here, what we are having is cathodate chamber. So platinum is cathode. So we can write T minus is equal to loss in cathodate chamber or compartment. Compartment, I will write compartments divided by total loss in both compartments. So what we have already have the total loss as well as loss in a cathode chamber. So we will be getting P minus is equal to 0.222 divided by 0.806. What's the value? What's the value coming? 0.2754. Okay, slightly different, so that's fine. So we can write T plus is equal to 1 minus T minus, which is nothing but 1 minus 0.2754, approximately equal to 0.7246. So this is the transport number for Cu2 plus, or you can simply write TCU2 plus. Clear? So I'll switch off the video because I don't have lights here. Yeah. Is it fine? Yeah, yeah. Okay, okay. That's what I asked this NPTEL office. They told just write a mail to NPTEL team. They will let you know. Because I'm yeah, yeah. Have you written? Yeah. Okay. Okay. Descriptive. Okay. So there won't be problems. Okay, then it's fine. Is it clear now? Yeah. What about the usage of calculator? Okay, when I asked here, I think the correct representative was not here. They just told to write a mail to the NPTEL team. They will let you know. Yeah, like that. But I since I'm not registered for the exam, I have the ID and I just registered in NPTEL. So I don't see any calculator or something like that in the portal. I can't see anything like that. So is there any calculator in the NPTEL website for you to solve problems? Okay, okay. I haven't. Yeah, yeah, Shanti. No, no, NPTEL. You are getting a mail from NPTEL team, right? Every week. So you can write to them or you just log into the courses. There will be contact option. They just told like that. You just tell the student to write to us. We'll let them know. Maybe different courses, it can be different. That's why they told like that. I don't know. It's actually a course from ISER Mohali, right? So I asked in the NPTEL office here in IIT Madras. So they just told to write, tell the student to write directly with the course details and registration details. Hmm. Okay, okay. Hmm. Okay. Let me ask some BTech students here. They used to register for NPTEL courses for credit, but I don't know. Someone take. Let me put in group. So they might be knowing who are wrote previously might be knowing. Let me check that way. Anyway, some of one of you, two of you can write mail to the NPTEL team. So they will give a clarity. Can we use calculator like that? You can write to them. Yeah. Is this done? So we'll move on to the next question. It's very dark here. So the next question, as the temperature decreases, the electrolytic conduction, hmm, as question has temperature decreases, electrolytic conduction increases or decreases. What's the answer? As temperature decreases, electrolytic conduction increases or decreases. Yeah, why? Why it decreases? Yeah, the answer is at higher one part is solubility. So at higher temperature, the solubility increases and hence the movement of ions. That is ionic dissociation, all those things increases. Then the mobility of ions increases like that. As temperature decreases, electrolytic conduction also decreases. So last week there was a uh, point H plus, Li plus, Na plus, K plus. Then we have transport number. So we had highest transport number for ionic mobility, rather ionic mobility or transport number 5. Highest for H plus, then we had Li plus to Na plus, there was an increase. So have you any of you tried to find the answer for this? So there is a specific trend here, right, for all these three. I don't remember the values, but from Li to Na plus, there is a gradual increase in the values and conductivity. So what's the reason? Why H plus has very high ionic conductivity? It contains only one proton and one electron, right? So it comes from something called Groth's proton hopping mechanism. Proton is very small, so what happens is it can attach to a water molecule and it forms something like H3 plus O, H3O plus. Okay. So what happens? There will be a proton comes, there will be a water molecule, so something H2O, H, H. So it will hop. From this side, it will hop to another one like that. It can propagate and moves faster. This is because its size is very small. So another water molecule will be the H, H, something like this. So it's called Groth's proton hopping mechanism. So due to this, H plus have very high ionic conductivity. Whereas in this case of lithium, these are alkali metals. So they always exist with something called hydrated sphere, hydration sphere. So suppose it will exist, you can write like Li, something like Li H2O 6 times whole plus. So as the degree of hydration decreases with ionic size. So as we go down, the size increases. This hydration sphere or degree of hydration decreases. Since as you can think like this, if you are you are holded by 10 people, it's difficult for you to move, right? So if it is by 5 people, you can somehow push them and move. Like that, as the size of the molecule atom increases, the hydration sphere, the degree of hydration decreases. Hence, the ionic mobility increases. This is why we are seeing a trend like increase in ionic mobility as we go from Li plus to K plus. So for H plus, there is a specific mechanism called um, Groth's proton hopping mechanism. So I thought it will be covered in this week's lecture. So uh, I was waiting for that. So that's the clarification for this portion. So now let's move on to this week's content. So what we have seen first is the variation of conductance with concentration. So what is the relation we have? Lambda is equal to 1000 L by C. So as we dilute the solution, what happens? Lambda increases, right? As we dilute the solution, lambda increases. But this relation is not same for strong electrolyte and weak electrolyte. So what's the difference? For strong electrolyte, how will be the, if you plot lambda versus root of concentration, how will be the plot? As you already told, lambda decreases with increases with dilution. So how will be the plot? It will be a straight line like this. It will be linear one. So if we extrapolate it up to the y axis, we will get lambda 0 or lambda 0 at infinite dilution. So I will write it lambda 0 infinity you can write. So we'll get the value. For a strong electrolyte, we have a relation lambda C is equal to lambda 0 minus B root C. Clear? But for a weak electrolyte, what we have seen, for a weak electrolyte, it is no longer a linear relation. So it will be something like, it decreases like this. So if we similarly, if we extrapolate here, we can get the value of lambda 0. That is conductivity at infinite dilution. Can I get a 1 minute break? Okay. Yeah, sorry. So it won't be a straight line if you plot lambda versus root C for a weak electrolyte. So this relation we can use for one is sufficient. Yeah, this relation we can use for the calculation of uh, lambda at a particular concentration. I will see a problem in the coming today itself. So next one is we'll see. We have seen one law. It's very important for calculating. It's a easy thing to for calculation problems and all. So it is called as law of independent migration of ions. What is that? Do you remember? What is called as law of independent migration of ions? If we take different, suppose KCl, NaCl, then KNO3, something like KNO3, then NaNO3, then KBr, NABr. So what's common here? If you take these two, the cations are same. Similarly, here also the anions are same. Again, here anions are same. So always say the difference between lambda 0, that is equivalent conductance at if infinite dilution, values of different salts with same anion are the same. So what does it mean? So if we take uh, lambda 0 KCl minus lambda 0 NaCl, the value will be equal to lambda 0 KNO3 minus lambda 0 NaNO3, which will be equal to lambda 0 KBr minus lambda 0 NaBr. So specifically, if the cations are same and anions are same and cation are changing, the difference between their equivalent conductance and infinite dilution will remains the same. So this is a one relation we need to remember. Then we can write lambda 0. Suppose we take NaCl, lambda 0 that is equivalent conductance at infinite dilution for NaCl. We can write it in terms of we can write it in terms of ionic conductance, which can be written as L0 Na plus L0 Cl minus. where lambda 0 KCl, similarly we can write L0 K plus L0 K plus L0 Cl minus. So what will be the value of lambda 0 KCl minus lambda 0 NaCl? What will be? It will be L0 K plus minus L0 Na plus. The idea is when we have weak electrolytes, we can find the ionic conductivity or equivalent conductance uh, in terms of, we can write it it as a combination of weak strong electrolyte, and for strong electrolyte we can easily find out what's the value of conductance and all, because they follows a linear trend, whereas the weak electrolyte does not follows a linear trend of conductivity versus concentration. So that's the idea why we want to convert the equivalent conductance. Hmm. Hmm. The idea of taking difference of this ionic equivalent conductance. So next one, what we have seen, formulas are just important for calculating many of the problems. So, all right. Similarly, we can find a relationship between ionic conductance and transport number. So there was a for what is it derivation for that. I won't go in details. So we have written lambda 0 is equal to L0 cation plus L0 anion. L0 are, what are these? Ionic conductivity. So if we take mm, detail, L0 cation is equal to K1 N plus Z plus into E into U. E is nothing but unit charge. We have seen in the last lecture, unit charge. Similarly, L0 anion is equal to K2, some other constants, K2 N minus Z minus E into U. So if we consider the charge neutrality, we can write these terms except U. These are equal. So we will write both as a same constant K, or simply K1. So we can write lambda 0 is equal to L0 cation plus L0 anion, which is nothing but K1 N plus Z plus E into U plus V. So now we will take a ratio L0 cation divided by lambda 0, which is nothing but U by U plus V, which is equal to transport number of cation. Then similarly L0 anion divided by lambda 0, which is nothing but T minus. So we can write from here L naught C is equal to lambda 0 into transport number of cation, and L naught anion is equal to T minus into lambda naught. Okay. Similarly, if we do some calculations, we can also find that this K1 is equal to K2 is equal to K, which is nothing but the Faraday constant, 1 Faraday. So we can write from here L0 C is equal to nothing but F into U. Similarly, L0 A is equal to F into V, where U is equal to T plus naught lambda 0 divided by F, and V is equal to T0 minus lambda 0 divided by F. So what does it mean? So speed at infinite dilution can be determined from transport number at infinite dilution and lambda 0 of the electrolyte. That's what if we have the speed at infinite dilution, if you want to find the speed at infinite dilution, we can use the transport number data as well as lambda 0, that is nothing but the equivalent conductance at infinite dilution. So there is some this terms L0 cation as well as L0 anion depends upon temperature as well. someone have given a what do you say, empirical for a relation for this, which is nothing but L0 25 degrees centigrade into 1 plus 0.02 into T minus 25 degrees centigrade. Temperature is in degree centigrade, so you have to take care of that. Yeah. So we'll just see one or two quick problems, otherwise it will be too much of theory. So given equivalent conductance of CH3COONA, NaCl, HCl are 83, 127 and 426 Siemens centimeter squares per gram equivalent at 25 degrees centigrade. Calculate the equivalent conductance of CH3COOH at infinite dilution. This is a problem, sir, written in the, I think, first class or something. So, all of you solved it. Can you try? What's the answer coming? So, I can write lambda 0 CH3 COOH is nothing but lambda 0 HCl plus lambda 0 CH3 COONA minus lambda 0 NaCl. So how can I explain how it's coming? So we'll just try to expand it here itself. So how can I write L0 H plus L0 Cl minus plus L0 CH3 COO minus plus L0 Na plus minus L0 Na plus minus L0 Cl minus. So these two will cancel out, and similarly this and this will cancel out. So like that you will get for acetic acid. So how can I write? It can be written as 426 minus plus 83 minus 127. What's the answer? What's the answer? What's the equivalent conductance at infinite dilution for acetic acid? So it's coming. You should always specify the unit. 382 Siemens or more Siemens centimeter square plus gram. So I don't have space. Gram Siemens centimeter squares per gram equivalent. Fine. So like the next question. Q. Calculate the ionic mobility of cation in a 0.1 molar solution of NaCl at 25 degrees centigrade given T plus is equal to 0.39 and lambda 0 NaCl is equal to 127 Siemens centimeter squares per gram equivalent. So let's try to solve this problem. So what's the answer? What's the formula we have to use? What's the formula we have to use? Anyone? What's the formula? U is equal to T plus 0 into lambda naught divided by F. So what will be it? 0.39 into 127 divided by 96485. Answer is, what's the answer? So once a problem is given, if it's solved, you just post the answer as previous. According to that, we'll move. So what's the answer coming? Yeah, the answer is 5 point unit. What's the unit? What must be the unit? It is centimeter squares per volts per second. So you just need to, because here current is ampere is there, resistance is there, ohm. So V equal to IR. V equal to IR, right? So what is that? This is Coulomb. Coulomb is nothing but ampere second. So ampere is current, this is second. So this is volt, this is ampere, this is ohm. So if you cross relate these things, you reach in the unit of centimeter squares per volts per second. That's it. So what's the next question? At, oh sorry, at 18 degrees centigrade, the mobility of NH4 plus and ClO4 perchlorate ion are 6.6 into 10 raised to minus 4 and 5.7 into 10 raised to minus 4 centimeter squares per volts per second. Calculate the equivalent conductance of NH4 ClO4 and the transport number. So how will you solve it? What's the basic relation we have? So we have lambda 0 is equal to L0 NH4 plus L0 ClO4 minus, right? So how will you write this? K into U plus V. Clear? So in the previous part we have written K is nothing but F. So the values of ionic mobilities are given. So it's straightforward. So what we can write, lambda 0 is equal to 6.6 plus 5.7 into 10 raised to minus 4 into 96485. So it is nothing but 118.68 Siemens centimeter squares per gram equivalent. Clear? So now you all can calculate the second part. Ionic mobilities are given. So yeah. So T plus, for others I'll write T plus is equal to U by U plus V, which is equal to 6.6 divided by 6.6 plus 5.7, obviously into 10 raised to minus 4 here, into 10 raised to minus 4 here. So we'll cancel out. So I won't write it. 0.537. So T minus will be equal to 1 minus 0.537, which is nothing but 0.463. Fine. So the next portion covered was applications of conductance titrations. So in that there are two types. First one was different type of acid base titrations. Then second was precipitation. Hmm, titrations. In the first case, what all we have seen, first one is strong acid versus strong base. Then second one is weak acid versus weak base. Then the third one was weak acid versus weak base. Then fourth one was weak dibasic acid versus strong base. What's the example for one? One of you. What's the example for strong acid versus strong base? Can you tell an example? So what we have discussed in the class. HCl versus NaOH. So second case, weak acid versus strong base. Acetic acid is a weak acid versus Na sodium hydroxide. So what will be the case of weak acid versus weak base? You can write CH3COOH acetic versus ammonium hydroxide. Then fourth case, we have already seen this part in the pH calculations, volumetric titrations we have done. So this is nothing but we can write carboxylic acid COOH versus NaOH. Then the second type of titrations are the precipitation titrations. What is the example of precipitation titration? What is the example? Precipitation titrations. Example was KCl versus AgNO3. So as you all, may have noticed, in this one only, the plot of the plot of the lambda versus volume of AgNO3 was having a different shape like this, it was going right. So this is the equivalence point. Similarly, for all the examples in the class, it was given how the conductivity versus uh, volume of NaOH or volume of AgNO3 added. So that plot was given. Mm. So I think all of you will go through that, so it is clear also. So last topic I'm going to, because we have to solve a number of problems. That's why I'm also going in a fast manner. So last topic, the final class derivation I'm not touching here. You can go through that. You can derive 2 or 3 times. You'll be clearly understanding that. So it's just substituting here to here. Then the activity and gamma and Fi gamma I as well as F. These relations are found out there. So how we are relating those things, it's given there. So last topic we will touch here will be degree of dissociation. Degree of dissociation. Then it is applicable for weak electrolytes. Electrolytes. Because strong electrolytes, it will be completely dissociated. If you put HCl, it will be like H plus and Cl minus. But if you write for CS3, COOH, we will write it like this. CS3, COO minus plus H plus, right? So I'm directly writing the formula. And we will consider the equivalent conductance of lambda C at a concentration C. So we can write degree of dissociation. Alpha is nothing but lambda C divided by equivalent conductance at infinite dimension, which is nothing but lambda C divided by L0 cation plus L0 anion. So there is one more thing called dissociation constant. So dissociation, suppose we will have a reaction HA, which is weakly dissociating as H plus and A minus. So we can write C into 1 minus alpha if the the degree of dissociation of the standard form, then it will be C alpha and C alpha. So what will be the dissociation? K alpha is equal to, you can write CH plus CA minus divided by C of HA. So substituting, you will get some of the relations, and we will get a limiting case also. We can write K alpha is nothing but lambda C square into C divided by lambda 0 into lambda 0 minus lambda C. So you can write it as K alpha is equal to, from here you can write K alpha is equal to alpha square C divided by 1 minus alpha. In the limiting case, most cases, alpha will be a very small number. So you can write K alpha is equal to alpha square C, or alpha can be written as square root of K alpha divided by concentration. So these are some of the relations we may need to solve problems. So now we'll directly go to numerical problems. The first problem is the equivalent conductance of 0.014 normal solution of ClCH2 COOH is 109 Siemens centimeter square, and the ionic conductance are 40.2 and 349.8 for, please take care here, for anion and cation. Calculate degree of dissociation degree of dissociation and dissociation constant for this one. This I'll write here ClCH3 COOH. So the equivalent conductance of 0.014 normal solution of ClCH2 COH is 109 Siemens centimeter square. And the ionic conductance are 40.2 and 349.8 for anion and cation. Calculate the degree of dissociation and dissociation constant for ClCH2 COH. So what are given here? What all values given here? Here given L naught C is equal to 340 L naught A. 340 root A of C. Okay, cation. L naught cation is equal to 349.8 and L naught anion is equal to 40.2. Then given lambda C is equal to 109 Siemens centimeter squares per gram equivalent. So can you tell what is the formula we have to use for degree of dissociation? What's the formula? Alpha is equal to what? Direct formula. Yeah, alpha is equal to lambda C divided by lambda 0, which can be written as lambda C divided by L0 cation plus L0 anion. So it's direct calculation. What will be the value? 109 divided by 349.8 plus 40.2. What's the answer? 0.279. So we got the value. So what next we have to calculate? K alpha is equal to what's the formula? Using alpha and not. Alpha and we have concentration also. Yeah, no, that is simplified version, right? Here we cannot write that alpha square C divided by 1 minus alpha. So what will be the answer? What? Alpha? Alpha is 0.279. So 0.279 square into concentration. Concentration is given in normality. So you can take 0.014 divided by 1 minus alpha. So that you get the answer 1.51 into 10 raised to minus 3. It will be coming in normal, or you can write mole per gram equivalent. Both are same unit, or getting clear? So the next question is the equivalent equivalent conductance at infinite dilution can be obtained from a plot of A lambda versus C, B lambda versus root C lambda versus C square, D lambda versus 1 by C. What's the answer? What will be the plot? Lambda versus root C. So how was the plots coming? It was lambda root C. For a strong electrolyte, we had a straight linear relation. As the dilution increases, as we dilute the solution, the equivalent conductance increases. We have this lambda zero value. For a weak electrolyte, we had something like this. So this is how we find out the uh, equivalent conductance at infinite dilution. Okay. So the next question is at 25 degrees Celsius, specific conductance of 2.54 gram CuSO4 solution per liter is 3.16 into 10 raised to minus 3 Siemens centimeter raised to minus 1. Calculate the equivalent conductance. Also you can find out what is the molar conductance. Here, so first equivalent conductance you have to find out. Similarly, molar conductance also you can find out. So what's the formula for equivalent conductance? What's the formula we have to use? What is the formula for? Lambda is equal to 1000 into L by C. So we have to find out C. For what is the first one is equivalent conductance, right? C is equal to what is normality? Weight by equivalent weight. So 2.54 divided by equivalent weight of what is it? Copper sulfate is 79.8, which is nothing but 0.0318. So what will be the value of lambda? 1000 into 0.0318 divided by, sorry, what was the value of L given? Okay, 3.16 into 10 raised to minus 3 divided by 0.0318. What's the answer? What will be the answer? 98.75. Okay, 99. Okay, so something, some small value changes. 98.75 Siemens centimeter squares per gram equivalent. So what will be the value of molar conductivity? How will you calculate it? Whereas concentration molar in terms of molarity, can write 2.54 divided by 159.6, which is nothing but 0.016. So same equation, lambda m is equal to 1000 L by C. Here C will be in terms of molarity. So it will be 1000 into 3.16 into 10 raised to minus 3 divided by 0.016. The answer will be equal to 197.5. Yeah, correct. Unit per mole. Good. So always take care of the unit, because here if I am taking in terms of molarity, the answer will be different. So here it's specifically asked for equivalent conductance. So we have to go for equivalent weight instead of molecular weight. Then only we will get the correct answer. So that's why I added in this question how to calculate the molar conductivity also. So when the equivalent weight and molecular weight are not same, the answer will also vary. If it is something like Ag and O3, the both answer will come same, or KCl it's come same, but in terms of CuSO or zinc sulfate, all those things, answer will be differing. So we'll go to the next question. So I'll plot a graph here. So to look at the following plot. According to Paul-Rasher's law, which is a strong electrolyte and which one is a weak electrolyte. So the plot is something like this. We have for that lambda versus root C plot. I have one like this. 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 So I name it as A, B, C, and D. So which will be the strong electrolyte? How will be the strong electrolyte behavior? C is a strong electrolyte. Which one is weak? Is weak electrolyte. We have already seen lambda versus root C plots. So it's straight line for a strong electrolyte. It goes like this for a weak electrolyte. So if you extrapolate, it will meet here at lambda 0. So the value may be different. Lambda 0 for weak electrolyte is strong electrolyte. So we'll move on to next question. Next question is little tricky one. So we'll solve it. The question is, if concentration is is increased 4 times of the original value, is C, the change in molar conductivity of a strong electrolyte is, I will give 4 options. 0, B is B root C, 2B root C, and D 4B root C. What will be the answer? So I have given B here, so I hope you will understand which equation we need to use. No, try to solve it. So one person is saying C is the answer. So try to solve. Others are also agreeing with the answer. Which is the answer? A, B, C, D. Others can comment also. We will solve it. But before that, okay. Smita is saying option D. So anyone else supporting Smita? Dilkush said option C is the answer. So any more answers? Okay, let's try it. Anyone else want to answer? So what's the formula? Lambda C. Okay, sorry. Yeah. Lambda C is equal to lambda 0 minus B root C. Let's consider concentration. Initial concentration was C. Then I'll for denoting it, I will use it as C1, and finally C2. So C2 is equal to 4C1. So how will we write? Lambda C1 is equal to lambda 0 minus B root C. We'll give it as equation 1. So lambda C2 is equal to lambda 0 minus B root 4C. So How will you find out change in molar concentration? We'll take mod lambda C2 minus lambda C1. So what will be the answer? Just subtract and see. What will be the answer? It's all change in molar concentration. So it will be D root C. So when we see directly, we'll see think like it's a root answer, right? So the question asked is change in molar conductivity. So we have to take both molar conductivity and take the difference. So that's fine. So we'll go move on to the. I hope everyone understood this problem. So we'll move on to the next question. It is also a little like fun like question. The equivalent conductance of Na2SO4, K2SO4, KCl, HCl, then HCOO, at 300 Kelvin or 260, 308, 150, 426, 105. These values I'm giving it as a table. What are these values? 300 degree centigrade. Now calculate lambda 0 of formic acid. See what will be the lambda 0 of CH3 COOH. I'll give 5 to 10, a little longer time. So just need to think and solve this. It's very simple. Lambda C, sorry, it's not acetic acid, formic acid. Lambda 0 HCOOH equal to what? H is equal to 1. So can you try to solve this? Are you able to solve this? How can we write this? Lambda 0 HCOH will be equal to L0 H plus L0 COO minus HCO minus formate plus proton. How will you expand this? Anyone solve this answer? What about all of you? So let's try it. Are you able to solve this? Anyone? Dilkush, Shanti, Manshu, then who else? Lavanya, Smita. Anyone? Bhavani, Durga. Anyone solved? So we just need to think about the combinations. So we can write. We have five different things. What is it? Na2SO4 is there, K2SO4 is there, KCl, HCl, and HCOONA. These kind of problems can easily come in exam. So we'll solve it slowly. L0 HCOO minus plus L0 Na plus. This is nothing but lambda 0 HCOO minus half into L0 2Na plus L0 SO4 2 minus. This is nothing but half into lambda naught Na2SO4. Then plus half into L0 2K plus L0 SO4 2 minus. This is nothing but half lambda 0 K2 SO4. Then minus L0 K plus L0 Cl minus. This is nothing but lambda 0 KCl. Then plus L0 H plus L0 Cl minus. So you can see here Na plus and these terms will cancel out. These two will cancel out. Then these two will cancel out. This will cancel out. What remains? This is nothing but lambda 0 KCl. So what remains? Which is nothing but L0 HCOO minus plus L0 H plus, which is nothing but lambda 0 HCOOH. Fine. So how will write? Lambda HCOOH, sorry, lambda 0 HCOOH is equal to lambda 0 HCOO Na minus half into lambda 0 Na2SO4 plus half into lambda 0 K2SO4 minus lambda 0 KCl plus lambda 0 HCl. So just need to think and write the combination. So what will be the answer? Because you see here, two sodium ions are coming. Na2SO4, how it will be? Na2SO4 can give 2 Na plus SO4, 2 minus, right? So this 2 we have to take into account. That's why it's half. Here, in these things, here, you're asking about these things. Okay, that's simple combinations. Simple combination means we have to think. What we have to find out? It is lambda 0 of formic acid. Formic acid I have written here. It can be written as L0H plus plus L0 HCO minus. So we have to get only these two terms. Yeah, and answer is not correct. Something went wrong in between. So please recheck it. So I'll come to Shanti's point. Yeah. So in order to get this combination, we have to try trial and errors. Trial and errors means you have to think a little and write it down. So there is no direct formula for writing like this. We have to write combinations so that whatever extra comes in the whatever given here HCONA is given. Our answer is 405. HCONA is given. From that, we will get HCOO minus. So there is one Na plus extra came. So for cancelling out the Na plus, I have subtracted this second term Na2SO4. So Na gone, a sulfate came. So in order to cancel that sulfate, I again took K2SO4. So when I use K2SO4, SO4 minus is eliminated, then again K plus came. So in order to eliminate that K plus from the formula, I use KCl. So in this case, K plus is gone, but Cl minus came. So in order to eliminate that Cl minus, I have taken HCl. So when I took HCl, Cl minus is gone, H plus is remaining. So what's remaining? HCO minus and hello? Yeah. Should I slow down? Yeah, yeah. So like that, whatever we have, we can find out the conductivity of strong electrolyte easily. Why? It has a linear relationships that it gives a straight line. So predicting the or experimentally finding out conductivity of weak electrolyte is little tricky. That's why we will write it as a combination of strong electrolytes. Understood? So what the values available is from that we have to slowly write like this. So the idea is what I explained. Like initially we need HCO minus, HCO minus that is anion. So from this we will get that. In that time, whatever extra coming, we have to use another one and subtract it. Similarly, uh, so what excess coming, we have to again use it. So this is little lengthy one. So I think the homeworks we have a shorter one, right? I think three only. Have you gone through the week six homeworks? Yeah, I think in the homework there is a shorter one. So what will be the answer? So it will be 105 minus half into 130 plus half into 308 minus 150 plus 426. The answer will be coming 405 Siemens centimeter squares per gram equivalent. Clear? So I'll go to the last question for today. Probably we'll stop with this problem today. Yeah. The degree of dissociation of 2HI gives H2 plus I2 at 500 degrees centigrade is this is question. The degree of dissociation. Degree of dissociation is nothing but alpha. We have to find out alpha for a particular reaction to HI reversible giving H2 plus I2 given dissociation constant is 0.483. So the degree of dissociation of 2HI gives H2 plus I2 at 500 degrees the question. So what's given is dissociation constant. Value is 0.483. Can you try to solve this? So what is the formula for dissociation constant? How can we write? What's the reaction here? 2HI is reversibly giving H2 plus I2, right? So suppose change in concentration C alpha and here also C alpha. What will be the change in concentration here? What will be the value? So this is the tricky part here. So here it is C into 1 minus 2 alpha. So how will you write K alpha? K alpha is equal to product by C alpha into C alpha divided by C square into 1 minus 2 alpha square. So it is nothing but alpha square divided by 1 minus 2 alpha. This is 2 by 2 delta beta. 1 minus 2 alpha square. So given K alpha is equal to 0.483. How can I write 0.483 is equal to alpha square divided by 1 minus 2 alpha square whole square. It can be written as alpha square is equal to 0.483 plus 1.932 alpha square minus 1.932 alpha. When we simplify, we can write 0.932 alpha square minus 1.932 alpha plus 0.483 equal to 0. It's a quadratic equation. So solution will be x is equal to plus or minus x is equal to, there will be two solutions, b minus b plus or minus root of b square minus 4ac by 2a. So either you can use a calculator. So make sure that alpha value cannot be greater than 1. You get two solutions. Probably one can be negative, one can be above 1, etc. So whatever comes within 0 and 1 only can be the solution. So what will be the value of alpha? You can use calculator also now. So, but while solving yourself, try to solve using this direct equation. Instead of x, I'll write this alpha. Yeah, alpha is coming 0.29. So last 2, 3 questions are little conceptual. So you have to practice it. Without that, is that clear? Any doubts in today's questions? So try to solve these kind of problems. I think there are there is one question similar to this in homework. So try to solve it. So anyway, in this kind of problems, next class starting, you have to solve for me. Like I'll try to give more problems like this so that all of you will be practiced in this. Is that fine? Yeah, probably we'll stop here today. So, as in mentioned, one or two of you write to